Welcome to an exploration of one of cryptography's most fascinating innovations, technology that allows you to prove something without revealing how you know it. This seemingly paradoxical concept is revolutionizing blockchain scalability and privacy, powering the next generation of crypto applications. Embark on a journey exploring the seemingly impossible challenge that zero-knowledge proofs solve, using intuitive analogies rather than complex mathematics. Learn how these cryptographic concepts work through famous Alibaba's cave example and other metaphors that make the complex understandable. Explore the future implications and opportunities as ZK technology matures and becomes integrated across the crypto ecosystem. Imagine facing a fundamental contradiction. How can you prove to someone that you know a secret, like a password, or that a transaction is valid, without revealing the secret itself? This is the core problem that zero-knowledge proofs, ZKPs, solve, and it's not immediately obvious how such a thing is even possible. The mathematical foundations are complex, but the concept can be understood through analogies. The explanation of zero-knowledge proofs uses the Alibaba's cave analogy, first described by cryptographers Jean-Jacques Quisquarter and others. Imagine a circular cave with a single entrance and a magic door at the back that requires a secret password to open. The cave branches into two paths, left and right, that both lead to this magic door. Peggy, the prover, wants to prove to Victor, the verifier, that she knows the password to open the magic door, without revealing what that password is. Peggy walks into the cave and randomly chooses whether to take the left or right path. Victor waits outside and doesn't see which path she took. When Peggy reaches the end of her chosen path, Victor shouts a random request: "Come out from the left path," or "Come out from the right path." If Peggy knows the password, she can open the magic door if needed and always come out on the path Victor requested. If she always succeeds, Victor becomes statistically certain that Peggy knows the password, even though he never learns anything about what the password actually is. The zero knowledge in this is that Victor learns absolutely nothing about the password itself. He only becomes convinced that Peggy knows it. The key properties of zero knowledge are illustrated here: completeness, soundness, and zero knowledge. These interactive protocols have evolved into non-interactive versions in modern ZKP implementations. Beyond the cave analogy, zero-knowledge proofs have real-world applications such as authentication without passwords, private transactions, anonymous voting, and blockchain scaling. These applications represent a paradigm shift in what's possible in cryptography, moving from trust through transparency to trust through mathematical proof. They enable a secure way to prove a complex equation without having to do the full calculation yourself. One of the promising applications of ZKPs in blockchain is ZK rollups, a Layer 2 scaling solution that addresses Ethereum's throughput limitations. Ethereum can process only approximately 15 transactions per second, leading to high fees and congestion. ZK rollups process thousands of transactions off-chain, then generate a single, compact ZK proof that all transactions were valid. This approach is fundamentally different from other scaling solutions because the mathematical proof guarantees validity without needing to trust the Layer 2 operator. ZK rollups work by bundling user transactions together and processing them off-chain. The operator creates a cryptographic proof that all state transitions followed the rules of the system and were applied correctly. This proof, along with the compressed transaction data, is submitted to Ethereum in a single transaction. If valid, Ethereum accepts the new state as final, enabling efficient scaling. Several leading projects are advancing ZK rollup technology, focusing on EVM compatibility and user experience. ZK-SYNC, developed by Matter Labs, offers a seamless Ethereum experience with minimal modifications. StarkNet, created by Starkware, uses a different proving system called Starks for greater scalability. Polygon ZK EVM is another project focused on full EVM equivalence, allowing Ethereum contracts to run directly. These projects are paving the way for more efficient and scalable blockchain solutions. ZKPs enable true privacy on transparent blockchains. One of the most powerful applications of this technology. Zero-knowledge proofs allow you to selectively reveal information on a need-to-know basis, even on a public blockchain. This solves one of cryptocurrency's fundamental tensions. Blockchains are radically transparent by design, yet users need privacy for practical and personal reasons. Privacy-focused ZKP implementations include Zcash, Tornado Cash, and Aztec Network. Zcash was the first cryptocurrency to implement ZK snarks for private transactions, allowing sender, receiver, and amount to remain hidden. Tornado Cash uses ZKPs to break the link between sender and receiver, enhancing privacy. Aztec Network offers a privacy-focused ZK rollup for Ethereum, allowing confidential smart contracts. These implementations demonstrate how ZKPs can transform public blockchains into platforms offering privacy and security. Each type of ZKP has distinct advantages and trade-offs, making them suitable for different applications. ZK snarks require an initial, trusted setup, ceremony and are used in Zcash and most ZK rollups. ZK Starks are scalable and transparent, requiring no trusted setup, and are used in StarkNet and Immutable X. Bulletproofs offer compact range proofs without trusted setup, used in Monero and confidential transactions. The field continues to evolve rapidly, with new constructions appearing regularly that improve on previous limitations. Generating proofs requires significant computational resources, making it time-consuming for complex operations. Some ZK rollups currently need specialized hardware to generate proofs efficiently. Creating ZKP circuits is complex and requires specialized knowledge, and the tools and languages for ZKP development are still maturing. Proof size and verification time can be prohibitive, but recursive proofs and specialized hardware acceleration are helping to overcome these challenges. Recent breakthroughs include recursive snarks, which allow a ZK proof inside another ZK proof, creating a recursive system that enables infinite scaling. Plonky 2, a proving system from Polygon, generates proofs extremely quickly, bringing ZK rollups closer to real-time performance. ZK EVM equivalence allows Ethereum contracts to run directly on ZK systems, dramatically simplifying adoption. Hardware acceleration designs for ZKP generation can increase speeds by orders of magnitude, potentially transforming the industry. As the technology matures, zero-knowledge proofs extend far beyond cryptocurrency and blockchain. Digital identity can be verified without revealing sensitive information. Sharing medical information with providers can be done securely without exposing personal data. Supply chain verification can occur without revealing proprietary supplier relationships or pricing information. Machine learning models can be trained on informative data without revealing the training data itself. These implementations showcase the versatility of ZKPs across various domains. As ZKP technology becomes more efficient and accessible, we can expect a paradigm shift where privacy becomes the default rather than the exception. ZK Layer 3 networks build upon ZK rollups to create application-specific scaling solutions, all secured by Ethereum. Hybrid privacy systems combine ZK technology with other privacy techniques to enable sophisticated privacy-preserving applications. Specialized hardware in consumer devices dedicated to generating and verifying ZK proofs can bring privacy-preserving computation to the edge without relying on cloud services. ZK systems that can prove AI models adhere to ethical guidelines and security standards will transform AI governance. Several projects are advancing zero-knowledge proof technology, each with unique contributions. Polygon ZK EVM aims to achieve full EVM equivalence, allowing existing Ethereum smart contracts to run unmodified with ZK proofs. StarkNet uses Stark-based proofs for quantum resistance and no trusted setup. Aztec offers a privacy-focused ZK rollup enabling confidential smart contracts on Ethereum. Scroll focuses on using open-source components to bring back the Ethereum ecosystem. Mina Protocol uses ZK snarks to keep the entire blockchain at a constant size, enabling access on mobile devices. Zero-knowledge proofs represent one of the most profound breakthroughs in modern cryptography, a genuine, magic trick that seemed impossible before its invention. ZKPs transform the transparency of blockchains, which are inherently public, into an asset, allowing for verifiable computation without revealing underlying data. The implications for blockchain are transformative, potentially solving the fundamental trilemma of decentralization, security, and scalability that has confounded the industry. Subscribe to follow the development of zero-knowledge technologies powering the next generation of crypto applications. Explore interactive ZK circuit playgrounds, hackathons, and curated ZK resources. Share your thoughts and join the conversation about the future of privacy and scaling in blockchain. What do you think is the most powerful application of ZK technology?